My name is Jesse Burns. I'm a principal partner with Information Security Partners. We're a security consulting company, and I'm based out of San Francisco. I'm going to talk today about fuzzing selected Win32 inter-process communication mechanisms. I'm going to focus on just a few of them because there's a huge number. And what's a Win32 IPC mechanism is one of the things I'll cover, but I'm looking more at things that are specific to Windows programming, not Berkeley sockets type stuff. So I'll be starting with a little bit of a background of fuzzing and some information about Windows IPC. Then I'll talk about mechanisms for identifying the communication channels to test. Turns out that determining the attack surface of applications isn't always obvious. And I'll cover a couple of tools, give some demonstrations, and then I'll jump into a mechanism that requires a little coding. That's doing it with code hooking and using that for finding name pipes, which kind of leads into using that for testing name pipes and for testing generally any kind of IPC mechanism, with name pipes as sort of the example. And then I'll jump into another mechanism, which is shared sections, just kind of briefly. And there's going to be demos throughout. And I should say that we've got sample code. There's a zip file on this CD, which is floating around. And there's code on our website, which I'll give you an URL for in a little while. The code has different components in different languages. All of it compiles with Visual Studio 2005 Express Edition, which is available free of charge. And all of it's available under pretty liberal licenses. Our code's under GPL. Some of the dependencies that we use, like Matt Conover's libraries, are available under a BSD license. And these are our public fuzzing tools. They just kind of give you all the examples that we're doing here today, and I think a few other things. So what's fuzzing? A little introduction. Fuzzing is when you take some program that you have and you have data that it accepts. Maybe it accepts usernames, and it's expecting a string, maybe a 1 to 10 character ASCII string. And instead of giving it a 1 to 10 character ASCII string, you give it the worst possible thing you can think of. You give it really big strings, you give it null strings, you give it multi-byte data, you give it Unicode, every bad character you can think of. Just throw it all at it and see what it does. If you have input, you want to know if providing bad input can cause your application some problem. Generally, your program is going to have two kinds of input. It's going to have input that it trusts and input that it doesn't trust. The real difference here is difference between the two is whether or not the person providing it or the entity providing it has an identity relationship with the service process. And so if it runs as the same account, well, you don't have to worry about it. If it runs as some other user, even if the other user is also a low rights user, you do, because you're going to have access to things that it doesn't have access to. So software binaries themselves are actually, you could think of as trusted input. So that means they have to be ACLed correctly. Obviously, when programs have bad ACLs, attackers can overwrite the programs, and when trusted users run them, they're exposed. Scripts, libraries, all the inputs to a program from a database, if the database itself is the thing that the program protects access to, that's usually trusted. Untrusted is where it gets interesting. That's anything that comes over the network, obviously. Anything that comes from files that aren't ACLed. If you download my PowerPoint slides off the website, or this zip file filled with tools that I'm recommending you download, open up and run, maybe recompile, all that's untrusted input. And you should be careful where you accept it from. So when you're doing security testing, we want to make sure that we trust all the vectors into our application for untrusted input. We want to make sure that no matter what comes in there on these untrusted channels, you can't crash the application, you can't cause buffer overflow that's exploitable, you can't make the CPU go to 100% and stay there for a half hour, you can't make it allocate all of its memory. Then you can also use you can also do this kind of testing on trusted inputs, but that's just really robustness testing. It's not the kind of stuff that we do at ISEC. But you can actually use fuzzing for both kinds of input. And if you find some issue, great. That's nice to have, especially if you're integrating it into your QA testing. It's good to be able to get some additional benefit. So A lot of Windows IPC is based on securable objects. And securable objects are this standardized design that Microsoft has for kernel objects. So when you get one kernel object, like a socket, it's got a lot of the same attributes as a file, or as a registry key, or as a named pipe, or a section. All these objects have features that are the same, and they have things like discretionary access control and mandatory access control, that's auditing. So if an administrator knew that a certain application used name pipes, they could go in there and they could say, oh, I'd like it to audit whenever someone fails in their attempt to access this. In practice, most administrators have no idea what IPC channels are being used on the system, but it's a nice to have, and it's great for, when you think about it, in the future, HID systems, things like that, might start instrumenting these things and using those kinds of things. So one of the other things that's true about these IPC channels is that some of them are only accessible locally. So a lot of the privilege escalation risks that I'm looking at are going to be local host privilege escalation. So I've got a low rights account and I want to make it into a high rights account. I've got a low rights account and I want to take out the service that reports my bad behavior to the system administrator. Anything like that, that would be local. But there's also a remote aspect to these, especially with things like name pipes. They can be accessed from any machine on the network, and you have to be a little more careful with them. If you don't intend to have it used remotely, then you have to specifically ACL it so that it can't be used remotely. And that's not too hard to do, but it requires a little bit of effort. And it's often not done. So one of the other interesting things about these Win32 IPC things is they tend to be highly compatible between versions of Windows. You can find that NT3.1, the first version of NT that was multi-user, like the first version of Windows that was multi-user, has a bunch of similar IPC mechanisms to Vista. And you know, this stuff even works between NT and 2003 server. So so I'm going to just talk a tiny bit about what the attributes are that these securable objects share. So one of them is the discretionary access control list. The DACL is you know, the thing that you have to set right. If you have a multi-user system, which Windows is, and you're writing code for it, you absolutely have to secure it so that it's safe in a multi-user environment. You might not use your computer personally in a multi-user environment, but lots of people do. This is becoming even more important with Windows Vista, because under Vista, the default is that users run with low rights. Mandatory auditing is another feature of all securable objects. Again, rarely used, but it's certainly powerful. And owners. Owners are the little people that created the object, usually. You can end up being the owner of lots of interesting objects on your system. And you can always change the access control list, at least the discretionary one, if you're the owner of an object, which means administrators who try and lock you out of your own files by changing the ACL on them, well, they haven't done a very good job. So there's another attribute called integrity level that's new to Vista, which I'm not really going to talk about today. And then one other attribute is not universal, but occasionally occurs, is the idea of names. And names are a really important part of Windows IPC. Names like, I know you've seen files, so files have paths, right? Well, a path for a file is just a name. It's a shared object that's named. One of the nice things about naming an object is that you don't have to have an inheritance relationship with the process that created the object in order to access it. So if you have an anonymous pipe, you have to basically create a child that has access to the same handle. Well, with a name pipe, you can create a name, and then both those processes can open that pipe up. Now, names don't just apply to named pipes. They also apply to a bunch of other IPC mechanisms. And just because you can't type in dir on your command shell and see them doesn't mean they don't exist just as much. Obviously, registry keys have names, but mail slots have names. Mutexes can have names. Some objects don't have to have names. Like, it'd be pretty useless to have a file that didn't have a name, but there's nothing that says a semaphore needs to have a name. It's used for thread synchronization, and if it doesn't exist outside the process, if it's not used outside the process, there's no need to name it. And in fact, most of these objects aren't actually named, and they only really become part of the security surface of the application when they become named, unless you have untrusted children, which is a very rare condition. So, Here's a big list of some of the Win32 IPC mechanisms. Hopefully some of these are things that you haven't seen before, but maybe none of them are. Events, event pairs, files, keyed events, LPCs. LPCs are an undocumented but fast IPC mechanism. Some of these, like sockets, are never named. I mean, they have the idea of maybe a port associated with them or something, but they're not named. And they don't get part of the namespace. So I'm going to just focus on a few of these. I'm not really going to, I can't talk about everything here. I'm going to talk about some of the ones that are the most common. So probably the most common Win32 specific one is the named pipe. So named pipes are kind of like sockets. They're either UDP, or sorry, message mode or stream-based, which kind of looks kind of like UDP or TCP. They can be accessed locally or remotely. And the remote version is based on SMB. So just like sockets, you wouldn't expect when you open up a socket that you get any confidentiality protection on the data that you transfer over it. Well, just because you're using this thing that you found in the back of some book, this named pipe, doesn't mean you get any more confidentiality protection on it. You may, if you've got your SMB tuned up nicely, you might get some integrity protection at least. But determining that on a particular system, this configurations are just right so that it takes advantage of Kerberos authentication and Kerberos authentication only, or NTLM v2 authentication and NTLM v2 authentication only, and not some obsolete mechanism, and that it uses signing for all of the messages. Those aren't the kind of things that are easy to determine, and there's no easy programmatic way. So you just generally assume that, like you would with a socket, this data, when it comes in over the network, is totally untrusted. It might have been intercepted, and if you want confidentiality and integrity protections, you better layer them on top. Shared sections are a named block of memory. So it's kind of like an mmap, if you've used that system call. You get a region of memory, and you can map it into as many processes as you want. So really fast, and really a great way if you need to share your structs or something that you don't want to have to come up with a fancy way to marshal. And they have no they don't have a synchronization mechanism. With a named pipe, when you stuff a message down, on the other side, the read returns. Not so with a section. With a section, you just have a block of memory, and when you scribble in there, whatever you write is in there for anyone else who wants to look. And if you want to tell them, hey, you should go and look in there, you have to do it through some other channel. So because of this lack of synchronization, data validation can be really problematic, and we'll talk about that a little more later. But one of the other things that's nice about these, or not nice, but that's essential to understanding their nature, is that they're local only. You don't have shared sections across a network. There are systems that do shared memory across a network. It's inefficient, and it's inefficient relative to on a local host. So events are almost the opposite of sections, where sections just give you a message and no signaling. Events give you a signaling and no message. So when I have some event that occurs, I can wait for it. I can say, I'm going to wait on this event, and when someone pulses that event, I can say, all right, now it's the moment. It's just one bit of information, and that is that whatever the context-dependent thing that this event was associated with has happened. So you should wake up and do whatever you're going to do. One common use is you should read that shared section because I put a message in there for you. But you can do them. You can use them for just about anything, and they've got all kinds of nice APIs, like you can wait for multiple events and do things asynchronously with them. Semaphores are a thread synchronization mechanism, and all these objects can be named. I'm only interested really in named ones. One of the things that's interesting about naming a thread synchronization mechanism is that almost every thread synchronization protocol that you'll come across is cooperative. So there's no such thing as a trusted a thread synchronization scheme where you don't trust the other parties to try and not be creating bad deadlocks or whatever. So whenever you see a semaphore or some kind of thread synchronization scheme exposed with a name, you have to worry a little bit. even if they're local only, you better lock down those ACLs pretty tight, because if any other user can access them, there could be issues. So you can use them securely for things, but it's a big red flag. And what I look for from a design perspective when I see a semaphore being used in a named way is, who are the other people I'm sharing this with? Do I really trust those processes? Is there any identity or privilege gradient? We want to make sure that when we look at our process, we see all the different attack surfaces. And if this is in the exposed surface, then there's usually something going on here. Either this thing isn't being used for thread synchronization, it's being used for some other side effect, or there's probably an issue, or at least a substantial risk that you're accepting. So these techniques that I'm talking about have a couple of goals. One of the goals is to identify vulnerabilities, local or remote, in applications. We've got, as I've said a couple of times, some binary that we're looking at. Maybe it's some kind of service, and we want to make sure that every part of the attack surface of this application has been covered. And we knew, oh yeah, this thing listens for connections on port 25. We're used to that, and we know that it accepts files from users, and we've got a antivirus scanner, and we've checked the parsing routines in there. But when you're looking at it, you have to also see, hey, are there any additional surfaces, attack surfaces, places where input come in that I'm not aware of? And you might be surprised how many of those you find. I know that when I ran the pipe list utility for the first time, I was kind of surprised to see 80 or 90 pipes jumping out on my laptop, which is just running PGP disk and maybe some VMware and stuff. And there's this huge number of pipes. Anyway, so we want to identify local or remote vulnerabilities for privilege escalation. Localhost privilege escalation is the main one, but remote would be good too. So our secondary goal is that we want to work on applications in binary form. So we've got all these libraries, COM objects, dependencies, operating systems that we don't have the source code for. Or if we do have the source code for them, they're so big, we don't have time or energy to go through them all. Even if there are bugs in them, they're not our bugs. We don't necessarily want to go through the hassle of understanding them all. It's a very common security auditor's dilemma. We just want to be able to trust the things that we can't review. And so working on binaries is going to be a really important part of that. Also, these test tools that we develop, we're going to spend a little time putting together some tools for testing, and they should be as integratable into the regression tests and reusable in the testing process as possible. And they should be as static as possible. Once I'm done building this thing, I'd like it if I didn't have to change it just because I added one more interface or I've changed the protocol a little bit. If you make a nice fuzzer that knows the protocol and speaks it really well, if you change that protocol at all, you have to change your fuzzer so that it can test the new parts of the protocol. One of the things that we'll be doing is making ours a little bit more independent of what actually is being communicated. And that's going to allow us to minimize the change to our tools for new versions of the software. It's going to allow us to reuse this fuzzer on all kinds of different products. So, unfortunately, fuzzing isn't a silver bullet. Ideally, we'd of course want to find any kind of bug, but in practice, we're limited to certain types of bugs. So obviously, the ideal bug would be something that crashes the application. Application crashes don't go unnoticed. You can get your postmortem debugger to pop up. If you have some exceptions, that's great. Good logging would be the next best thing. Anything that puts the system into an inconsistent state, screws it up, makes the CPU spike, uses up all the memory, that's going to be good enough that probably if you have a real tester sitting there looking at the machine or an automated set of tests that expects the tests to finish within some reasonable amount of time or with some reasonable maximum CPU load, you'll be able to detect it automatically. So what kind of bugs are good for this? Well, we definitely want to target applications written in C and C++. These tend to have a lot of technical bugs that aren't application domain bugs. By application domain bugs, I mean, if you have an application that does some type of complicated function that, maybe it grants access to a checking account, right? figuring out what's going on inside that domain isn't very reusable because the next application you look at isn't using checking accounts, it's a video game or something. So fortunately, there's this huge class of bugs that afflict all software, and they're things like integer overflows, heap and stack overflows, pointer problems, any type of memory corruption issue. And these are also great because the operating system works proactively to detect the conditions. If you write to some offset in memory that's chosen at random, the odds are you're going to get a protection fault and invoke the debugger. So makes it easy to detect, makes it easier to debug because the errors occur in a way that sort of points to what's the cause of the problem. And some of them are a little trickier, like with parser bugs or double free bugs. You can get a lot of conditions where the code crashes a long time after the actual corruption occurred. And certainly with fuzzing you find a lot of those, but they tend to pop up later in the development life cycle, or later in the testing cycle. So maybe with your first pass, you find a bunch of the more obvious bugs. And then as you go on and the thing starts making it running longer with the fuzzer on it, then you start running into these kind of harder corner cases, and that's not as big a problem. So the bugs that this is no good for are these domain-specific bugs I was telling you about. So I've used SQL injection as an example here, but SQL injection, actually, if you've got the right kind of application-level auditing, like say you have application-level auditing that reports SQL errors whenever a SQL statement is submitted that doesn't parse, right? Oh, the syntax is wrong in this statement. That's exactly the kind of debug code you should have in your application. It's exactly the kind of warning you need to know about. And in the QA phase, this is going to make the fuzzer could actually find some SQL injection issues. Command injection is a lot harder. If it does run a command, the odds are very low that it's going to be something that makes sense. The best you could hope for is some kind of systrace thing. It's not really happening. Authorization bypass. As you can imagine, if you've got some kind of authorization scheme, like check to see if this is the right account before you take the money out of it, right? And some fuzzing allows you to bypass that. It's not going to find it. Authorization bypass, a whole bunch of these bugs, basically things that are in the domain of the application itself, aren't going to be detectable. Also, backdoors, any kind of intentional bug. So when a developer decides that they are going to put in a little present for themselves if they ever have to retire, those types of bugs can be found basically through source review only. You're not going to find them accidentally through fuzzing. And then the security and design bug where, oh, we decided to implement this really bad idea. Like, oh, what my application does is it waits to see if it's Friday, and if it's Friday, it decides to go look on the internet and see if, oh, this website has a posted zip file with a number greater than the number of the last one I downloaded, installed, and ran. And if it does, I'll run it. That kind of poorly designed, insecure automatic update scheme may respond very well, fuzzing isn't going to show any problems with that. It's the design that's screwed up there, not the implementation. You can have a great implementation of that terrible design. So, naming and creation attacks. So these naming and creation timing attacks are unfortunately closer to the domain of the IPC mechanisms themselves and still can't really be found. These are design issues again. So name squatting attacks are when, if you have a client that connects up to a server, and the way it finds it is it connects to a name pipe named foo. And it says, oh, foo, tell me what to do. And the server says, oh, get these updates. You need new antivirus signatures. You need whatever. And it just trusts it. Well, a name squatting attack is going to be very effective if the attacker can run code before the server reserves the name. It can also be a real problem on a network, because if it's going across the network, as I mentioned before, those clear text protocols might not give you integrity protection or confidentiality protection. An attacker might decide to set up their own server with the name of the server that you think you're going to and put a pipe on that. So that's that name squatting attacks. These fuzzers won't help you find those kinds of bugs. Races prior to DACL establishment. So when you create an IPC object, you've got two options. You can either set the ACL right then, or you can add the ACL later. And yeah, it might seem like kind of a bad idea to add the ACL later, but it's somewhat popular. And it creates race conditions. If you've got this thing that anyone's allowed to connect to just for a few milliseconds, that's when the bad guy will connect. So these would be great bugs to be able to find. And I'm very glad to say that we can't find it because then I can keep my job. So, but I wouldn't be giving this presentation if they could, I guess. So, viewing of IPC objects. So when we're first looking at IPC objects, you kind of got to get a feel for what these things are. You may be surprised to find out that components you're using or libraries that you're using or software that you've installed uses some of these mechanisms, and you never knew it. And you might even be surprised to find that they don't ACL them correctly or ACL them in a way that you wouldn't consider secure. There's a company called sysinternals that makes some great tools. When I wrote these slides, they weren't. They were a separate company. Now they've been bought by Microsoft. So these tools are available right now on their website, though, and are great. One of them is called Process Explorer. Process Explorer. Well, I'll show it in a minute. Another one's called Handle. It's a command line version of Process Explorer that's kind of less powerful, but it's good for parsing its output if you want to like use it in programmatic, like maybe you want to write a little Python script that digs around on your system and finds IPC mechanisms to test. None of these tools are affiliated in any way with ISEC. We're just big fans. And you know, you can kind of think of some of these tools like a super version of LSOF for Windows, if you're familiar with that Unix tool. So here's a picture of, oh, I wonder if I can actually point here. Here's a picture of Process Explorer, and you can see I've got the call logger here. I've selected it, and when you select it down on the bottom, you're getting a list of all the handles that it has. And the handle I've highlighted is one that's called Device Named Pipe Call Logger. And I've asked for the properties, and then I've asked for the security properties, and then I've gone into the ACL. And this lets me see, oh look, everyone's in that ACL. Fortunately, that everyone is read-only everyone. But it lets you just dig in, and you can go by process. Oh, I'm worried about this particular process. Oh, I'm worried about you know, this particular section, and dig through and see which processes are using it. It's pretty good. And then handle. Here's the exact same thing, only with the command line version. So with handle, you can see the same call logger process being accessed. -p call logger tells it to find that call logger program. And you can see the file there, device name pipe call logger. And it's actually got the handle ID, which, you know, it's not quite as much information as you got with the GUI version, but it's good. So, what are these tools good for? Well, they're really great for getting started understanding the Windows IPC mechanisms. So if you are looking for communication across a privilege gradient, especially communication that's not trying to hide itself across a privilege gradient, this is a good place to start. They also get you thinking about what the ACL should be and let you kind of browse around and see what they're doing. You don't need any source code, so they're a real good way to get yourself kind of familiar with it. If you're going to do any programming with these types of things, you definitely want to play with these a little bit. It gives you a feel for what you're using. But they're not the right tool for short-lived objects. If I've got a named pipe that, you know, say I have a mail slot on my machine, and when someone connects up to it, I tell it, oh, here, connect up to this named pipe, and I give it a name, and I create that named pipe, and they connect, and we do a really quick couple of back and forths, and the whole transaction takes 10 milliseconds. I'm not going to be able to see that in Process Explorer. Even if it showed it on the screen, my eyes aren't that fast, and even if they were, my brain's not that fast. So totally the wrong tool for looking for that. But it's also not directly useful for fuzzing. It's good for identifying attack surface, and it's good for understanding the problem. So, more complicated, powerful tool. WinDebug, standard Windows debugger, totally multi-purpose, and you know, this is just one more thing it's good for. You can get it for free, which is nice. All these tools are available without charge. And it can intercept your kernel 32 calls that create all these IPC mechanisms. And that's really what we want. For name pipes, there's the create name pipe function. For shared sections, there's the create file mapping. And you know, I've got a little picture there of it seeing something. I'll show you a demo in a bit. I think it's probably the same image. Let's see, so what's good about Win32? Well, we're able to use this to actually alter program behavior. So instead of just seeing the IPC mechanisms, now we can actually set breakpoints on the creation of these IPC mechanisms and change the calls. If I want to change the parameters, I can just go right onto the stack and say, oh, you know, this pointer that you were pointing to this name, I'm going to point it to somewhere else. Or, oh, that memory that pointer pointed to, I can just change it in place. So they're useful for manipulating, very slowly, the creation of objects manually. So you can sit at your keyboard, and I guess if you're paid hourly, this might be a good way to go. It's certainly good to go a few times just to get the feel for what you're doing. Breakpoints, you know, we can extend the life of breakpoints. So if I've got that little problem I was talking about where when the client connects, the whole transaction only lasts 10 milliseconds, well, I can slow this down to an amount of time that I can actually read and you know, think about what's going on there. Also, one of the great things about Win32 is that you can configure it as the post-mortem debugger. So whenever your fuzzer causes a crash in the application, poof, up this pops, and you've got the whole process memory, you've got the registers, you've got the stack, all there. You can save it to a file. You can hand it off to a developer. If you're going the I want to make a patch route, you can hand it off to them, and they can look at the stack and figure out what went wrong. If you're going the I want to write an exploit route, it's got all the offsets, and you're ready to go for writing your exploit code. What's not so great about it? Well, it's not really very graphical. I mean, it's maybe a little graphical, but it's not. It's kind of hard to start out with. And actually examining the contents of ACLs, you know, you've got this untyped information like, oh, here's what's on the stack. How many of these are actual parameters to this call? Why don't you look in MSDN? And then you can figure out what the calling convention is and, you know, figure out what all these parameters are and change them. So not exactly slick. And it's very difficult to use for direct fuzzing because of the manual nature. So, using Win32 to intercept the creation of name pipes. So, we can do this for a couple of reasons. One is to discover IPC mechanism use, which is really still more of a feeling it out kind of thing. Or, you know, it can also be used for if you want to create a log of the SDDL. I don't know if you know about security descriptor definition language, but SDDL is a kind of semi-human readable way of describing the ACLs on a securable object. You can dump that, for example. And you can also use it to hook the IPC mechanisms for fuzzing. So I'm going to give a very brief demonstration of using it for discovery. So this is the very simple part. Fire up Win32, verify that my symbol path points to my symbols directory. The symbols that I have there are just the public symbols off of the MSDN public symbol server. So nothing special here, nothing related to the code. Then I'm going to open the program I'm going to test. This program is called Call Logger, and it's included in the ISEC public IPC fuzzing tools that are on that little CD and available on our site. And I think Black Hat will make them available. And as soon as it starts up, what you see here, you can see that? Good. Is we've got a little command shell going, and we've hit a breakpoint right off the bat. And this breakpoint just lets me do things like set other breakpoints before the actual application starts to run. So in here I'm going to say breakpoint kernel 32, bang, create named pipe W. I don't know if I mentioned before, but create named pipe, there's two versions of it, the W and the A. The A stands for multi-byte character set. Actually, it's stood for ANSI, but remember, it's not ANSI, it's multi-byte character set. Those things can be international characters now. Didn't used to be. The W stands for wide-car, and those are Unicode characters. And all the A's functions do is convert the multi-byte character set to the wide-cars and call the W's. So if you're hooking functions, stick with the W's and you're in better shape. Doesn't matter then what the program itself is doing. So okay, we've set a breakpoint. we take a look at the list. Sure enough, there's a breakpoint sitting there. So we're going to continue the program. And the first thing the program is going to do is listen on a name pipe by calling create name pipe. And sure enough, that causes our debugger to return without any output from the actual program itself. And we can take a look at what's on the stack. So it's a little command that shows what's on the stack. You can see here that the first couple of arguments are on the stack there. And the very first argument, if we looked in MSDN to create name pipe, is the name of the pipe to create. So I figure this must be a pointer to it. So I type in here du, which displays a Unicode string from a memory address. Type in the memory address. And poof, out pops the name whack whack dot whack pipe whack call logger, which is indeed the name of the pipe that I'm creating. So that's using WinDebug to see IPC mechanisms getting created. So that was possible, but not ideal. All we had to do was stick the breakpoint in, and up it pops. So the most interesting thing about doing this is that now that we understand it, we can build on it by automating it. So, middle person fuzzing. We might want to use a similar technique to actually fuzz this name pipe. So say we had an application, a server, that was going to create a name pipe named foo. And what we could do is we could use WinDebug or some other mechanism to intercept that call and change it to bar. Then we could launch our own name pipe named foo. And when clients wanted to connect to the server, they'd connect up to foo, and we'd forward the data to bar. So I'm going to illustrate that a lot more later. But we don't want to do it with WinDebug. We want to do it with something that's going to automate it so we can reuse our testing tools and we don't have to sit there and type all day. So we're going to use some code injection and hooking tools. And there's a bunch of them that are available. There's probably the first one. There's a good paper about it from Microsoft Research. It's called Detours. And it's a pretty powerful little system for doing this. There's, it's under a commercial license, however, and the commercial license is kind of pricey. So might not be good for trying out on the weekend. There's Matt Conover's BSD licensed x86 hook, which comes with a whole bunch of other utilities. It's not just a hooking system. It comes with things for regular expressions. It comes with things for services. It comes with a bunch of security code. It's really powerful. You can do disassembly. You can do all kinds of stuff. There's an URL for it. It's free, so that's what I've chosen to use for these demos. There's the API Hook SDK, which is a commercial product. That's available for a small charge. I haven't actually used it. And there's Mad Code Hook, which I think is kind of cute because it's written in Borland Delphi. And lets you hook stuff, and I programmed that in the 90s, so that was fun. Then there's the other option, and the other option is to do your own homegrown ghetto detours implementation. And some people like Scott Stender and Andreas Winstam from ISEC have done that. And if you're that kind of adventuresome person, go ahead. But my goal here is to do this quickly and not to necessarily explore the world of hooking. So I'm just going to use Matt's excellent code and leave those other ones be. But certainly different libraries might be appropriate for you. So, hooking injection. Hooking, it turns out, it's much more powerful than just for a fuzzing IPC. You can use it for all kinds of things. You can use it for HIDs. You can use it for making your own ghetto version of strace that filters the parameters of system calls. You can do lots of cool stuff with it. Usually when you build a hook, one of the things that all those libraries do is they package it into a DLL. And DLLs are just the Windows shared library scheme. When you package your code into a DLL, it's easy to load in and it's easy to unload. It's easy to put initialization code in there. It's easy to get notified when threads attach or detach. So it's a really handy way to be able to do that. And my code, of course, is packaged into DLLs. As I mentioned before, the source is all available for all these demos. And they're all written in C. Can't really I mean, you might be able to do something like this in Python, but C is the right language. So what we're going to do is we're going to use hooking to discover IPC mechanisms. We're going to do the exact same thing we did with WinDebug, only instead of setting a breakpoint, I'm just going to hook the API. So I'm going to use a program to inject my hook in. The hook's going to replace the start of create name pipe function with a little piece of code that says log out what pipe we're going to be writing to. So it's the equivalent of that DU statement and the looking up of the parameter on the stack. And then it's going to print that out. We'll see it, and we'll be all happy. One of the other things here is that we could have logged the ACL. We could take the ACL, convert it to SDDL, and log that. This is sort of a, that would be more for if you had a big set of tools that you wanted to go through and make sure, hey, every product that my company offers properly locks down the ACLs it exposes. And you might want to make something like that that was more general than just for name pipes. And that's pretty easy to do, actually, because these hooks are really non-intrusive. For that, probably have to talk to us or do it yourself. So I'm going to just do a little demo where I inject this hook into, I think, the same process. Maybe I'll use a slightly different program. Does the same thing, creates a name pipe, and I'll just log out the name so that we can see that we're doing it with code injection. And one of the things that you'll notice about this example is that it's going to be a lot easier to do. And so if you're actually doing this day to day, it's not going to be as boring, and it's going to be totally reusable, and the program is very short. So the first thing I'm going to do is, yeah, here we go. Okay, so I've got a program here called tHookProc. That's part of Matt Conover's code injection tools. It actually doesn't recompile very well with Visual Studio 2005, so I recommend using the binary build of that. All the rest of this stuff does compile with Visual Studio 2005. And the reason why you want Visual Studio 2005, of course, is that there's the free Express edition. You can see here that I'm running a program called listenonpipe.exe with a parameter which is name of the test pipe. Maybe not now. Name of the test pipe, and the name of the test pipe, that's the pipe it's going to create. So my library that I'm going to inject is called namedpipespy.dll, and that's the thing that has my hook in it that's going to overwrite the start of create name pipe. So I run that, and down in the window where I executed it, you see a whole bunch of stuff coming out of the tool that hooked it, just saying, oh, that worked, because I practiced this demo. And it works. This little window that popped up is actually the listen on pipe process. And what it does is it just says, hello there, I'm going to be using this name. My PID is foo. Press enter to begin listening. And so when I hit enter, it's going to start listening on that name pipe, and our hook's going to become activated. So I better run the program to log the output. So now I've got this call logger started. Call logger is just a program that's going to receive the message. So when I hit enter, over on the call logger, I see the name of the pipe appear. So this little string that said name of test pipe Bob. So I can create any number of pipes and have that log them all. Now, if I wanted to make it a little more interesting, I could include SDDL and other information about the pipe that said what the ACL was that it was created with, so that you could figure out if this was part of the attack surface of the program. Remember that even pipes that only allow one connection at once and immediately have the client connect have a race where users with low rights users could try and connect up to it. Oh, and those low rights users could be remote. So, injecting a middle person. So now that we've injected a spy, we can think about injecting a script in the middle. The script in the middle is going to do something like hook the creation of the IPC mechanism and launch a fuzzer and move data back and forth. So the normal flow is you have a server, and the server wants to create a name pipe to let clients connect up to it. So it says to the kernel32, hey, I'd like to create a name pipe. And the pipe's name is foo, and the kernel says, sure, here you go, and it gives it a name pipe. And then the client connects to the pipe, and everyone's happy. Well, when we've got this hooked, the flow changes a little bit. The server calls kernel32 and says, I'd like to create a name pipe named foo, and the hook receives the call instead of kernel32. And the hook says, well, I'm going to just launch this middle person script. So it does a shell exec on a Python interpreter in our example here. And now we can write our actual fuzzer in Python, which is a lot easier than writing a fuzzer in C++. You have, it's just a easier language to do string manipulation or fuzzing. My partner, Scott Stender, is going to be doing a presentation this afternoon on internationalization attacks. And one of the things he'll do is talk about, he's got some code where he shows a bunch of different ways of doing car set attacks. Really cool stuff. You could take those car set attacks right out of his Python code and dump them into this, and then use that fuzzing technique on this attack surface. What the middle person fuzzer does is it goes ahead and it creates the name pipe that the server wanted. So it says, hey, kernel32, can I have a name pipe called foo? Sure, says the kernel. Then the hook says, all right, I'm going to just change the name of the pipe that we create on behalf of the server to bar. And then this operating system gives the actual server back a different pipe. Now the server doesn't know that it's been given the wrong pipe. It just thinks that, oh, my call succeeded. I know I passed in foo. If it wants, it can go and look in that buffer and see if it's still called foo. It is. We didn't actually change it. But the client doesn't know that the name of the pipe has changed. And so the client still connects up to foo, and the fuzzer just forwards the reads and writes along to bar. And optionally, it can modify them. And actually, it can even tell which ones it should modify. It can tell, for example, if this is a read-only pipe, that the only thing that's worth modifying is the output, right? And so you just modify the output. If it's a duplex pipe, so it allows information transfer in both directions, which is one of the flags in the mode that you specify when you call that create name pipe function, then it can modify just the input and fuzz the server. And if you want, you can tweak the Python script so that it's targeting the client instead of the server. So I'll give a little demo of this. I'm not actually going to exploit some piece of code and have a 0-day here. I'm going to just do a little fuzzing demonstration on a sample server. So I'll set up a little server that just shows the data that it's receiving from its client, and I'll set up a little client that writes data to it, and we can see that the data is being modified by the hook. Oops. All right. So I'm doing the same thing I did before with the T-hook proc. I'm launching listen on pipe. This time I'm calling the pipe test pipe, and I'm injecting, instead of the name pipe spy DLL, I'm injecting the name pipe redirect DLL. That's my little C hook that changes create name pipe so that instead of just calling or creating a name pipe, first it launches a Python script, tells the Python script, hey, here's the new name and the old name of the pipe, what the modes were, what the, which direction the data is going to be flowing, any parameters it needs to create an equivalent version of the pipe. Then my script creates its own pipe, and the hook changes the name of the pipe that the server is going to create to something else. In this example, it appends underbar original to the original one and lets the client create the one that was expected. Sorry, the fuzzer create the one that is expected by the client. So when I run this program, the first thing that happens is that listen on pipe.exe pops up. This is my listening program. So this is my server down here. The actual hook is just reporting back, yes, I successfully injected myself and it's been activated. So when I hit enter here, it's going to start listening on a name pipe. And so I expect that what's going to happen is a Python script is going to be spawned that is going to be doing the fuzzing on any data that goes through this pipe. So I hit enter, and up pops this little window with a happy little snake in the corner. And the window says, hello there, this is the Python script spawned by the hook. I'll be accepting client connections from whack whack test pipe, and I'll be redirecting the reads and writes to whack whack test pipe original. And it logs a seed, which is useful for resuming the fuzzing, and lets you know that the client pipe's been created. So now we need a client. Here's the server. This works better on a high-res screen. So my client is just a tiny little program that writes to any particular pipe, any file, once a second. So the file I have here is abc.txt. It's the alphabet. So you can easily spot if it's changed anything. And I think it's in all uppercase. So it's going to just write that once a second. So I hit enter, and up in the server, immediately we see the alphabet being sent once a second. And it doesn't look quite like the alphabet that I would normally expect. Maybe this one right here is totally unchanged, but I've got a very high change rate, so I'm doing a lot of random fault injection into this data that's coming in. Now, in an actual example, you might lower the chance of the injection occurring, and you might change the injection so that they have things that are specific to the domain of your application, but you don't have to. You can just go with this. And if I kill the client, it stops, and when I restart the client, oh, you'll notice that over here in the hook, I got a little exception, but now it's resuming because I restarted it. So as long as I send and receive data in here, I'll keep getting little exceptions in the hook, and the pipe will keep seeing fuzz data. All right. So one of the things that's nice about this approach is that the Python code at least, or actually all the code is fairly simple, but the C code's simple because you don't have to rewrite it every time. You can just reuse it over and over again. The Python code's also totally reusable if you want to do the simple kind of thing that I've done here. If you want to do some customizations like adding in Scott Standard's internationalization fuzzing, you can do that by just changing the Python, and the Python script can be actually really simple. All you need to do is create a named pipe with the name that's passed in, listen on it for connections. When connections come in, pass them off to the server, make any changes you need. And so what kind of fuzzing do we want to do? Well, we just need to decide what we want to change. So the obvious and simplest thing to do is just randomly inject faults. Change random values. It says A, I say B, whatever. Maybe shorten and lengthen the strings randomly, which is one of the other things this does. You can try incrementing and decrementing values. That's really helpful for looking for fence posts. Inserting large numbers, so it's really good to write at least one, all binary ones into every offset inside of the message, at least once when you fuzz it. So you might even do it in a window to move through, because what you're looking for is things that take offsets, untrusted offsets. Like people move structs sometimes through these things, so that's not safe. You might want to overwrite all the nulls to see what happens when strings get really big. You might want to overwrite the double nulls to do the same thing with Unicode. This is all standard fuzzer stuff. You can do anything you want. You can change the size of the writes so that they're enormous. You can null them out. You can do things like look for a username, and when you see the username occurring anywhere in there, add some garbage. Mix it up. The ideal rate of change lowers over time. So when you first start fuzzing out an application using this, you might find that if it's fruitful, you might find that you get bugs right off the bat. And as the engineers come back with you with patches, usually you want to lower the rate of change so that you can get deeper into the protocol. If you've got a sophisticated protocol with a lot of different messages going back and forth, you might need to get in pretty deep before you inject the fault if you want to find kind of deeper errors in the logic. Usually when you inject something that the server isn't expecting, it's just going to close the connection on you. So, if you never let it get very far without injecting an error, you won't get it to fuzz the deep parts of the protocol. Another tip is to all these fuzzers are based on something random that you do. Well, it's not really random, it's pseudo-random. So that means if you restart with the same seed value, you can generate the exact same changes to the input. So if you use the same data set, you run the same server, you use the same seed, you should get the exact same flow. That's really important for reproducing bugs. Now, sometimes you're going to have things like, oh, this thing's based on, this thing's I don't know, it's some kind of weather satellite monitoring application, and every time it looks, the atmospheric conditions are different. So the data is always different, and so you can't actually repeat it that way. Well, that's fine. Another technique you can use is just log all the traffic that travels through the pipe. Say, oh, the server said this, the client said this, here's a transcript. And then you can actually just write a very simple script to replay the client side of the transcript. And you can sometimes do fault injection. I think in the sample tools that I ship, there's a simple pipe fuzzer that doesn't actually relay a transcript, it just kind of writes random junk, but it's the same kind of idea. You could do that and base it on what the simple transcript was from at least one side of the conversation. And then, I definitely would recommend using the injection to fuzz your applications as part of your automated tests. So that, if you found that, oh, sometime we once had a buffer overflow in this thing, or we once had some integer overflow issues, those get reintroduced all the time by accident. And if you keep, there's no reason not to reuse a tool like this every night. Just keep it running. So that kind of wraps up named pipes. I'm going to just talk about shared sections briefly. Shared sections are a different IPC mechanism. They're not as common, but you will probably be surprised if you run that handles.exe program pipe grep -i section. You might pipe wc -l. You might be surprised how many lines of output come out of it. You have quite a few shared sections on your machine, and these things are even more dangerous to share because, as I mentioned before, they're often named, so they're discoverable, so they can be used by other users, and they don't have an integrated synchronization scheme. So data validation techniques, like say I wanted to do a strlen on some string that was in the section to make sure it was no bigger than the buffer I want to copy it into, and then I do a stir copy, well, that's a serious bug because there's a race condition between the time I do the strlen and the time that I do the stir copy. So that can be really problematic. A lot of functions aren't thread safe, and you don't want to mess around and hope that the implementation works the way that you think it works, and then when the next service pack comes out, find out that, oh, it doesn't actually guarantee that it works that way just because it happened to be. Or it works just fine on a uniprocessor machine, but on a dual core it has problems. Or, yeah, anyway. So if you don't have a guarantee of its thread safety characteristics, don't trust it. Usually shared sections are associated with some additional signaling message or mechanism, like an event or a named pipe. And we can discover them using the same techniques that we used for finding the named pipes, including the sysinternals tools. I've kind of covered this already, but the synchronization, usually these things are just convention-based, these synchronization schemes. So be on the lookout for synchronization-based conventions that are supposed to be secure. So two techniques for fuzzing these things. One's called scribbling. That's just pushing bad data in. And the other one's called asynchronous scribbling. And what this tries to do is, in addition to doing random fault injection, it also breaks the convention around when threads are going to be updating this. So we can take advantage of race conditions in the validation code and find those. So, how to scribble? Well, first thing you do is you start a test server running. You should run a test client at least once to kind of get the structures. Like when someone writes a message to a named pipe, it usually is just left sitting in the section. Sorry, when someone writes a message to a server through a shared section, the message is usually just left sitting in the shared section when it's done. So if you run the client a couple times, you can kind of prime it. Then you map the shared section into your fuzzer's address space, make a couple of changes, and start signaling the server, hey, try now, try now, try now. And you've got your WinDebug running. Maybe you've set as your post-mortem debugger by saying WinDebug -i. You should be able to find non-synchronization based issues with the parsing routines. Oh, problem with that is that you need to know what the synchronization scheme is. You can guess if the server's got one event and one shared section that they're probably related, but you don't necessarily know, and it could be something totally unrelated. It could be that the user clicks a mouse, or it could be anything. So not my favorite way to go. My favorite way to go is with the asynchronous scribbling. This one's more automatable because you don't need to actually understand how the server and client are talking to each other. You don't need to know the signaling mechanism. All you need to know is that they're using some shared section. So you take that shared section and you start writing into it. And you start a server and a client doing an automated regression. They're running through, doing a full functionality test, and you're just writing randomly into that shared section. And if there's any problems with their data validation or race conditions, the odds are you're going to hit them. That's the kind of, let's see. Yeah, that's the kind of fuzzer we have here. It's included in the tools that we're distributing. Oh yeah, we also included a C-types foreign function interface front end for this, for a bunch of Win32, or for a bunch of section-related Win32 things. This little fuzzer does is it takes the name of a shared section. I've got the target section is the name of this section, but you can try any section you want. And you can do things like random faults, -r, just puts random junk in there, null the whole thing out, max the whole thing out, so set everything in the section to 1 or 0, which can cause strange errors sometimes. If you see, if at any point a pointer is being read out of that thing, just by maxing it out, you can see that immediately. And that's sort of like kind of the very first layer of problem that you tend to see coming out of these things, like people have just marshaled structs back and forth in them, and we get a pointer out of there. And, so if that's happening, this will immediately find it. The same with offsets. If people are marshaling, here's an array and it's got an offset in there, well, you set it all to FFFF, and that'll cause protection faults. And we can catch those in the debugger and then figure out what's going on. The -L option just tells it to loop, so it runs this over and over again. And it's kind of boring to watch if it's not actually finding bugs. So I just put in a static screenshot. So defending against this, well, unfortunately, the big advantage of the shared section is that it's super, super fast. This doesn't take away from the speed that much, but I know you don't want to do it, but you have to copy the content of the shared section into some non-shared memory before you do anything with it. The very first thing your server should do when it receives that signal is not do data validation and make sure that the information's all, inside the spec that you expect. No, just take it and copy it. Then, once you've got it copied, you can look into it and see, hey, is there something in here that shouldn't be in here? Is this string too long? Whatever kind of data validation you do. Both the semantic and the syntactic validation that you want to do prior to passing it along to the application to generate a response. The other thing you should definitely do is consider locking down the ACLs on those. Often that's a design change and not the kind of thing that you can just patch into software, whereas this copying solution is. But it's certainly a better general purpose thing because it'll find the bug that you missed. So I'd like to just thank Scott Stender of ISEC for helping with this, and he's helped me a lot with my various Win32 IPC fuzzing stuff. Obviously, at ISEC, we've got teams of people that work together, and this stuff is based on the work that we've done for a bunch of different clients, and just generally, if you need help with this kind of stuff, feel free to give us a call. Any questions? Oh, yeah, go ahead. The way that so I'm using Matt Conover's the x86 hook library, and the way that it works is it overwrites the instructions, the first couple of instructions of the preamble with a jump into his library, and then his library actually allows a pre and post hook, as well as it gives you a trampoline back to the kernel 32 call. Actually, if you use his library, the hook function that I implement is the pre-hook, and it automatically passes the results through to the actual function call itself. So I can change the parameters if I want, but I don't have to. And in fact, I do have to change the parameters for the hooking one, but not for the spying one. Any other questions? Okay, well, thanks for, oh, yeah. Himanshu Dwivedi has them, and he's right down here. Maybe he comes forward. But there are also, the tools are available with an updated version of the slides from www.isacpartners.com. Any more? All right, thanks.